In this video, we will take a look at the so-called Gompertz mortality law. And we'll start by looking at this table of mortality rates in the US by age from 2017. I will provide the link to this table in the description of the video below. So in the first column here, it shows the age, and then the rest of the table is divided into male and female. And the reason for this is simply because the mortality rates are quite different. So in this example, I will focus on the male mortality rates. And in particular, we will focus on this second and third column, the death probability and the number of lives. First of all, let's take a look at this third column, number of lives. It starts with 100,000, and it shows how many out of 100,000 people born today will survive up to 1 year, up to 2 years, and so on. So for this reason, this third column is also called the survival function. So for example, if we scroll down here and look at 18-year-olds, we see that out of 100,000, 98,974 are expected to survive up to that age. So in other words, if you are born today, the chance of surviving up to 18 years is about 98.9%. Now in the second column here we have the death probability, and it simply tells you if you just turned 19 years old, what is the chance of dying in the next year. And here we see it's about 8 out of 10,000. Now, of course, these two columns are related to each other because if you compare this number at 18 and this number at 19 years of age, you see that 80 people out of this number here will die up to their 19th birthday. So this number here will be 80 divided by 98,974. Or in other words, a chance of dying among 18-year-olds. And what we are going to do in this video, we will observe this empirical observation called the Gompertz mortality law, which describes the second column, this death probability. And using that law, we will show how to model the survival rate, or the third column. So let's start by looking at the second column. So if we graph this death probability as a function of age on the logarithmic scale, we see that it follows approximately some linear trend, at least after a certain age, approximately after 30 years old. So if we zoom in here and look at the range between 30 years and 90 years, we see that this death probability can be approximated by this linear trend, and in this particular case this line is given by 0.0331 times the age minus 3.9. This is on the logarithmic scale, so this line describes the logarithm of age, and if you exponentiate both sides, you will get that the hazard function approximately follows this exponential 10 to the power c plus kt, where the constants c and k come from the trend line above. And it will be convenient to rewrite this exponential in base e instead of base 10. And of course you can do this just by writing 10 as e to the power natural logarithm of 10. So what you have to do is take these constants here, and if you multiply them by natural logarithm of 10, you will get minus 8.98 and 0.0762 for the exponential model here with the base e. And what the Gompertz law of mortality tells us is exactly what we observed above, that this hazard function, or the death probability, is growing exponentially in age, at least after a certain age, in this case after the age of 30. And this law was first empirically observed by Benjamin Gompertz in the early 19th century in England. And what we are going to do right now is to show that whenever the second column or the death probability or the hazard function follows the exponential, then the third column, which is the survival function s of t, as we said above, this is just the chance to survive up to the age of t. This function will have to follow the so-called Gompertz function, or this function s of t can be modeled by the so-called Gompertz function, which is given by some constant a times exponential of minus some constant b times another exponential of some constant c times t. And along the way, when we do this derivation for this model, we will also compute these constants a, b, and c for the particular data in the above table. And so we'll compare at the end how this model fits the actual data. So to derive this Gompertz model for the survival function, what we'll do first is start by looking at the derivative of the survival function. So if you approximate this derivative by the slope of the secant line, st plus 1 minus s of t divided by 1, we get s of t plus 1 minus s of t. And then I'm going to switch the order of these two terms and write it as minus s of t minus s of t plus 1. So s of t is the chance to survive up to age t, or the chance to live over t years old. And the second term, s of t plus 1, is the chance to live over t plus 1. And of course, this difference here is exactly the difference that we saw above in the table, right? It's the difference between two consecutive values, and it will give us exactly all the people that die between those two birthdays or die at this age t. So this difference is exactly the chance to die at age t. And then the hazard function, or this death probability, is exactly this chance of dying at the age of t, or the difference between two values in the third column, divided by the value at the third column, or the chance of living up to your birthday number t. And now the numerator is exactly what we computed above. This is just minus the derivative of the survival function, and the denominator is the survival function. So we see that the hazard function in the second column is related to the survival function in the third column by this formula minus s prime divided by s. And so now if we start with this formula, first thing we can notice is that this ratio s prime divided by s can be written using the so-called logarithmic differentiation formula. It can be written simply as the derivative of the natural logarithm of this survival function s. Of course, you can check this just by using the chain rule. The derivative of the log will give you 1 over s, and the chain rule will give you the derivative of s. On the other hand, since this is the hazard function, the Gompertz law, or that empirical observation above, tells us that this follows an exponential trend, that this should be equal e to the c plus kt as we saw above. And now, if we know that the derivative is equal to the exponential, then what is this function minus ln of s if the derivative is exponential? Of course, we can easily guess this because the derivative of exponential is exponential. So here we need this exponential, but because of the chain rule, the factor k will come out, we need to divide by k. And also we need to add some constant because the derivative of a constant is also 0. So in other words, what we did here is we found antiderivative of this exponential, which is also called indefinite integral, which we are going to study very soon. And then once you have this formula, you simply have to multiply by -1 and exponentiate both sides to get that the survival function is e to the minus constant times e to the minus this 1 over k times e to the c plus kt. And then instead of e to the minus constant, I'm just going to write this as a, another constant a. And we already know c and k, right? These were given by the linear trend function above. So the question is, how do we find this constant a? So for that, we are simply going to take a look at the third column in the above table and find what is the survival function at the age of 30. Okay, and in this particular case, it's 0.9737. And then if you plug in 30 into this model that we just found, we get that this 0.9737 should be equal to this Gompertz function. And since we already know c and k, from here we can find this constant a. Okay, so you can check that this constant a will be 0.98965. And if you plug it back into the Gompertz function, finally we see that the survival function is equal to this Gompertz function with constants a, b, and c given by these three particular numbers here. Okay, so what we showed is that the assumption that the hazard function or the death probability follows the Gompertz law or the exponential trend implies that the survival rate will follow this Gompertz function, and we found the specific constants in this Gompertz function. And now you can compare this model that we just computed, or this Gompertz function, multiplied by 100%. So here I'm graphing it on the percent scale instead of on the proportion scale from 0 to 1, with the actual chances from the table that come from the third column. And you can see that the fit is pretty decent, but of course it's not perfect. And the reason for that is that if you go back and take a look at the Gompertz law on that logarithmic scale, the trend, the linear trend, was not a perfect fit. So the actual hazard function, it fluctuates a little bit around the linear trend, and so this is reflected in this final difference between the model given by the Gompertz function and the actual data. And now, as an exercise, you can take the second half of the table for female mortality rates and try to see what kind of Gompertz model would you fit to the female survival rate, starting from the Gompertz mortality law, or in other words, by looking at the hazard function on the logarithmic scale and fitting a linear trend line.